Okay, in this video, I'm going to provide some tips for extracting a mechanism from a manuscript and also parameterizing a rate law using data from a manuscript. So I'm going to go through kind of a couple topics, actually more than a couple, 5 or so, kind of quickly. Okay, the first topic I'm going to go through is the constant stoichiometry diagram. So I've put one of these here. This is taken from a paper by Grabo and Mavrakakis published in ACS Catalysis. And this is a pretty common way to present a mechanism. It's a pretty common way to present energies. So if we look at this mechanism, from it we can extract mechanistic steps, and we can also extract their energies. So looking here at the different locations, here I have CO2 gas plus 3 hydrogen gas. That's going to be my reference point. Its energy is 0. If I go here, I have CO2 gas plus 6 adsorbed hydrogen atoms. If I go here, I have an adsorbed CO2. So I can use this to get all sorts of information. So first, how do I create a mechanism out of this? So each time I make a step, so here I have a step, 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 for example. What I'm recording there is the change in what's going on. So I'm recording the change going from one state to the next. So for example, I can write these changes are going to give me what the different steps are. So for example, step 1, this is going to be step 1 right here. This step is going to be 3H2 plus 6 star goes to 6H star. And I know this because if I look at the two endpoints to this step right here and right here, both of those have a CO2 gas molecule. So that cancels out, and the only thing that's really changing is that I have these 3 hydrogen molecules that are adsorbing to the catalyst and dissociating and forming 6 hydrogen atoms. Okay, so what I also can do here is get the energy of this step. So if I wanted to know that, I have this value right here is going to be my energy. This appears to be maybe 0.9, so the energy of reaction 1 is going to be about negative 0.9 eV. So I can read that off this diagram. So providing quite a bit of information. If I go through and look at some other examples, so step 2, that's going to be here to here. Actually, let me draw that differently. It's going to be here to here, so that's going to be CO2 adsorption. CO2 gas plus star goes to CO2 star. I could look at the energy of that. It's pretty small. This energy is going to go from about here, which we said was about minus 0.9, to maybe about here, which is about minus 1. So maybe the energy of that reaction is minus 0.1 eV. We could write that down. So we'd say here. Step 3 is going to be this step. So I have CO2 star plus H star goes to HCOO star, and then that's going to give me an extra star. Notice that the diagram doesn't explicitly tell me that I'm reacting a hydrogen. It doesn't explicitly tell me that I'm freeing up a site, but I'm writing that reaction because I know that that's what must happen, right? I have to have a balanced chemical reaction. So again, I could look at the energies here. We said that this is at about, this piece right here is about minus 0.1 or minus 1. That I didn't really draw that too great, but that's maybe minus 1.3. So the energy of this reaction is going to be about 0.3 eV. Now, in contrast to steps 1 and step 2, this reaction 3 has an activation barrier. So the activation barrier is going to be this amount. Again, I didn't draw those lines too great, but let's say that goes between maybe -1 and -0.15 or something like this. So maybe delta E act for this reaction is 0.85 eV. So anyways, this is how I can extract this type of information from this diagram. I could go through and do this for this entire mechanism. At some point I'm going to get to a place where I have a branch in my mechanism, where I go from this black to this red or orange or whatever color it is. I'm going to choose, if I was to do that, which I'm not going to do here, but if I was going to do that, I would choose the black route because it's lower in energy. All right, so going back and looking at these steps, so we wrote step 1, for example, is 3 hydrogen molecules dissociating to 6 hydrogen atoms. Note that this step is not elementary. For a step to be elementary, it would have to be able to happen in one process. 3 hydrogen molecules adsorbing at the exact same time and all dissociating at the exact same time, that's nearly impossible. That is not an elementary process. However, steps 2 and 3 are elementary. Those can happen as single molecular steps. Step 1, instead, is an example of a lumped step. It comprises 3 instances or 3 turnovers of hydrogen molecule adsorption. So, say it comprises H2 gas plus 2 star goes to 2H star multiplied by 3. So this piece here, this H2 plus 2 star goes to 2H star, that is an elementary step. So this lumped step 1 comprises 3 elementary steps all summed together. But because step 1 itself is not a elementary step, it should not be used to write coverage expressions. So we don't want to say, so do not do this. We'll say 0 equals CH2 to the 3rd times theta star to the 6th. Actually, we'll say KF1 minus KR1 theta H to the 6th. So theta H is equal to K1, this is an equilibrium constant, CH2 to the 3rd, theta star to the 6th, all to the 1/6 power. That's incorrect. If we are going to write a coverage expression, we want that to be on an elementary process. So instead, we would use the associated elementary process here, which is one of these instances. We would use this reaction. In this case, we would say 0 equals KFCH2 theta star squared minus KR theta H squared. So theta H is going to be equal to the equilibrium constant times CH2 and then times theta star, where theta star is not under that, not under the root. Okay, so that's various aspects on constant stoichiometry diagrams, and we also threw in there some lumping of steps. Another topic is energies. So often manuscripts are going to report energies, right? So it's a pretty vague term, and maybe not something that you're used to reading about unless you're talking about like something in physics, like kinetic or potential energy, or if you're a molecular scientist or engineer. In molecular science and engineering, energy, the term energy, usually refers to electronic potential energy, which essentially is the energy stored within the chemical bonds of the molecule. Not exactly, but for our purposes. or I guess for the sake of it, or for the sake of an easy definition. These values are often equal to either the electronic energy, which is the value I just told you, or maybe the electronic energy plus the 0-point vibrational energy. For our purposes, these values are almost always pretty much equal to, not identically equal to, but pretty much equal to the internal energy, delta U. In fact, we can usually say that delta E is equal to delta H, which is the enthalpy. So when you see those values for what we're doing, you can assume that those are equal to either internal energy or enthalpy, whichever one you need, to be honest. So we know that enthalpies are useful quantities, but typically we are looking for a free energy, so we would need an entropic contribution to that. We've talked a little bit about entropies when we looked at frequency factors. For example, when we looked at that lecture, we showed that frequency factors for surface reactions, so a surface reaction, for example, this reaction right here is a surface reaction. It happens entirely on the surface. There's no adsorption or desorption piece or any interaction with any fluid phase species. The entropies of those reactions can often be approximated as equal to 0, particularly in our purposes. We can make that assumption. We further said that the entropy of activation, or the activation entropy, which we denoted with this dagger symbol, we said if the reaction is, if it's a surface reaction, then we would call that also equal to 0. So I should show that frequency factors at S, delta S of reaction and delta S dagger are approximately equal to 0. For an adsorption reaction, these quantities are not equal to 0. So an adsorption reaction involves a gas or liquid phase species binding to a surface, and there is a distinct loss of entropy in doing that. We said that for an adsorption reaction, the change in entropy going from the gas phase to the surface phase can be approximated as being equal to the change in entropy of going from a 3D translator to a 2D translator. So we said that that would be S2D, S trans 2D minus S trans 3D. Trans stands for translational. That's for the going to the transition state, so the reactants to the transition state. For the reactants going to products, there's a variety of models that we can use. They're all valid, so it's kind of like pick whichever one makes sense for your problem. Some valid assumptions are that the gas molecule loses all of its entropy upon adsorption. In this case, the change in entropy of reaction is going to be 0 minus the entropy of the gas molecule, which is then going to be equal to negative entropy of the gas molecule. The entropy of the gas molecule can be looked up, for example, on NIST. Another model is to say that the gas molecule loses all of its translational entropy upon adsorption. So if we then say that the gas molecule is a 3D translator, which means it is free to move in 3 dimensions. And then when it hits the surface, it loses all of those degrees of freedom. In that case, we would say that the entropy of reaction is going to be equal to 0 minus the translational entropy of a 3D translator. The entropy of a 3D translator is equal to the Boltzmann constant times the natural log of the partition function of a 3D translator, and this is going to be in units of molecules, energy per molecule per Kelvin, or alternatively, R natural log Q, and that would be units energy per mole Kelvin. Okay, so here we said that Q is the translational partition function, and let's say that it's the translational partition function of an ideal gas. So if you've taken physical chemistry, you might have seen this before. We can quantify it. It's based on kinetic theory of gases. The expression I'm giving to you here, in this expression, M is the molecular mass, so units of mass per molecule, not mass per mole. B is the molecular volume, so the molecular volume is going to equal R, the gas constant, divided by Na. Na is Avogadro's number times T over P. This is also going to be equal to kBT over P. Also in this expression, Kb is Boltzmann's constant and H is Planck's constant. Another model that we can consider is that the gas molecule loses 1 degree of freedom, or 1 degree, I should say, of translational freedom. Upon adsorption, in this case, delta S of reaction is going to be S trans 2D minus S trans 3D. S trans 2D is going to look a lot like S trans 3D. It's going to be equal to Kb times natural log of Q trans 2D, or R natural log Q trans 2D, where Q trans 2D has a similar functional form as for Q trans 3D. In this expression, this A here, that is area, and it can be approximated as 1 divided by this L term, where L is the number of sites per unit area, which is a value that's typically known for a catalyst. Another model is to assume that the change in entropy due to reaction, which in this case is adsorption, is approximately equal to the change in entropy due to condensation. And this makes sense because if I have a gas molecule that goes to a surface, I mean, essentially it's forming or it's interacting with that surface. It's adhering to the surface, and that's somewhat similar to what happens when a gas molecule condenses into the liquid state. It starts interacting with other things, other molecules. So the entropy of condensation, that is going to be equal to negative the entropy of vaporization. And then entropy of vaporization for many species can be looked up. For example, on NIST. So there's lots of different models for being able to take information or take energy values from a manuscript and convert it into these various different quantities that you may need. Another thing, though, that we should talk about are units. So many manuscripts are going to give units, energy units, in terms of EV, electron volts. So EV. When they do this, 1 EV implies 1 EV per molecule. So an EV is a molecular unit. It's a molecular energy. You can convert a value in EV per molecule to kilojoules per mole by multiplying by 96.48. That is not a very nice looking 96.48. So for example, if you see a value that's negative 0.8 EV in kilojoules per mole, this would be negative 77.2 kilojoules per mole. So it's essentially, if you want a quick estimate, you can multiply by 100. If you need a more precise estimate, you can multiply by 96.48. All right, the last thing I want to tell you about is the apparent activation energy. So an apparent activation energy is the activation energy. It's not writing that very well. That is observed in experiments. Usually they're obtained by creating an Arrhenius plot. So for example, I can plot the natural log of the rate constant versus 1 divided by the temperature. I get a approximately linear downward sloping curve, and then the slope is going to be equal to negative delta E app, apparent activation energy. So we denote it, divided by R. And I can obtain this information by linearizing the Arrhenius expression for the rate constant. So this apparent activation energy, what this implies is that multiple terms contribute to the activation energy. So for example, I have this hypothetical rate law. So the rate law for the dehydration of butane to butene, and I think this actually should be butanol. This should be the rate law for the dehydration of butanol to butene is this expression here. I have a forward rate constant times the partial pressure of butanol divided by 1 plus this capital KBU times the partial pressure of butanol. This capital, and that whole quantity is squared. This capital KBU, this is the adsorption equilibrium constant for butanol. At high partial pressures of butanol, so when the reaction just starts and not much products have formed, the partial pressure of butanol is going to be quite large. In this case, we would say that this denominator term, and I'm going to write this elsewhere because I didn't leave myself enough room, that this denominator term, that the 1 piece is going to be kind of irrelevant compared to the second term. So this 1 is going to be significantly less than KBU times PBU. In that case, the rate law is going to approximate an effective rate constant times the partial pressure of butanol to the negative 1. So in this case, this K effective is the apparent rate constant. So I could just as easily say Kf. Either way. And what it is equal to, or I guess I should say approximately equal to, this Kf divided by Kbu. And I guess that would be Kbu squared. So you can estimate a value of this Kf using the apparent activation energy as well as information from the electron frequency factors. So we know that the rate constant Kf is, or Kf, is going to be equal to some frequency factor times the exponential of negative delta E app over RT. We get this, get from the paper. And so then all we need to do is get this frequency factor. For a surface reaction, we said we can estimate those simply being equal to kBT over H, and that's because there's no entropy change. For an adsorption reaction, we said that those can be equal to P divided by L 2 pi mkBT. So that's going to give us a reasonable approximation. On the other hand, some papers are going to give you a frequency factor, so you wouldn't have to make those approximations. If that's the case, that's fine. But in the absence of that information, here's some models that you can use to do that.